Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous videos, we built the full intuition behind IV and 2SLS. Now let's derive the estimator and see exactly what IV is calculating under the hood. The derivation is surprisingly clean, and by the end of this video, you'll have a single formula that captures the entire logic of IV estimation, so pay attention. Recall the problem that we were trying to deal with. So we have a regression, a model y equals to beta 0 plus beta 1x plus an error term. We know that the covariance of x with the u is not 0. OLS fails because x is endogenous. And the OLS formula, so the beta hat OLS, which would have been covariance of xy divided by the variance of x, would have picked up the contamination. So we need a different approach. And recall the omitted variable bias derivation. The OLS estimator is going to give you basically the true beta 1 plus the bias whenever this covariance is different from 0. Now, IV is designed to eliminate exactly the bias term. So let's introduce the instrument. Suppose we have a Z instrument that fulfills the following condition. One, the covariance between Z and X is actually different from 0. So remember, this is the relevance condition. And secondly, the covariance between Z and the error term is equal to 0, meaning the exogeneity condition is fulfilled. So Z affects X, but uncorrelated with U, which means that the Z affects the Y only through X. And these are the two conditions that we need to derive the IV estimator. Keep in mind here we are assuming a just identified model since we have one endogenous variable and one exogenous variable, so both the rank and order condition hopefully have been fulfilled. The key insight is that because Z is exogenous, so the covariance between Z and the U term is equal to 0, you can use the Z to isolate the signal in X that is free from contamination. So the idea is that instead of using the covariance, so instead of using the covariance between X and Y, so remember the beta OLS formula, we were using the covariance between X and Y. So instead of using the covariance of X and Y to identify beta 1, which is obviously contaminated, we use the covariance of X and Z instead. Okay, so this is the fundamental IV move. We replace the endogenous variable X in the covariance formula with the exogenous instrument Z. So here Y. The formula with, so the exogenous instrument Z, and the substitution is what removes this bias. So let's start from the exogeneity condition to get to the actual formula. So from the true model, we have that the error term is equal to Y minus beta 0 minus beta 1x, okay? And given that the covariance of Z and U is equal to 0, what that means is that the covariance of Z and the entire expression that makes U, so Y minus beta 0 minus beta 1x, that is actually equal to 0. If we expand this, and keep in mind, we drop out the covariance for the constant because that is just 0, we will be left only with the covariance of z and y minus beta 1, because the covariance operator is a linear operator. And if you've forgotten all about the covariance operator properties, make sure you check the video on this playlist about the covariance operator properties. So beta 1 covariance of z and x. This needs to be equal to 0, okay? Rearranging it, we're going to have beta 1 being equal to the covariance of z and y divided by the covariance of z and x, okay? So it seems like pretty straightforward, pretty simple. It sort of has a resemblance to the beta IV, but now we're using the covariance in both the denominator and numerator, and we've got covariance of z and y and covariance of z and x, okay? So this is the IV estimator in the simple, just identified case, one instrument, one endogenous variable. It has replaced the formula covariance xy over the variance of x with something that uses z instead of x in the numerator. Okay, so the case where you had the beta OLS, you had covariance xy over variance of x, but this covariance xy was the problem because it was contaminated. So now this is not contaminated. Let's interpret the formula. We're going to break this formula actually in two parts. If you look at the numerator by itself, basically what we're checking is how strongly does the instrument affect the outcome. And the denominator by itself is how strongly does the instrument affect the endogenous variable. Okay, so in a sense, your beta 1 IV is actually effect of z on y divided by effect of z on x. So IV is asking how much does y move when z moves relative to how much does x move when z moves. And the ratio gives us the effect of x on y purified of the endogeneity problem. Okay, this ratio interpretation is crucial. If z barely moves x, in the case like where we have a weak instrument, the denominator in here is going to be very tiny, and the IV estimate is going to become very noisy. This is exactly why weak instruments are always so dangerous. Now, how does these all connect? So I'm going to write in here two particular cases, because we have a connection to what we call the reduced form and the first stage. Because if we're talking about effect of z on y or effect of z on x, that means that potentially we could run regressions where we can actually get betas for the effect of z on y and the effect of z on x. Okay, that's why we need what we call two auxiliary regressions. Okay, the two auxiliary regressions are the following. We've got reduced form And the reduced form is a regression of z on y directly. Okay? So we're imagining y equals to, let's say, gamma 0 plus gamma 1, z plus some error term r. Okay? And this gamma 1 hat here is the effect of z on x, on y. Right? And keep in mind, if we were to write this in the shape of OLS, this gamma 1 hat is basically covariance of z and y divided by the variance of z. The second auxiliary regression is the first stage regression. So this is a regression of z on x. For instance, x being equal to pi 0 plus pi 1 z plus an error term v. And in here, we need pi 1 hat being the effect of z on x. If we were to write the OLS shape for that, that is simply the covariance of z and x divided by the variance of z. Okay? So basically what we're saying is that our beta 1 IV is literally this gamma 1 hat divided by theta 1 hat. Okay? And if we write all of the formulas in here, you will notice that this is covariance of z and y divided by the variance of z, covariance of z and x divided by the variance of z, and the variance of z is actually going to cancel out, so we're going to be on covariance zy over covariance zx, which is exactly what we just set out earlier, okay? So in a sense, IV is simply the reduced form coefficient divided by the first stage coefficient. This, by the way, is also called the Wald estimator. Okay? Another thing that I would like to point out in here, especially in terms of terminology, because I know that that gets a lot of students confused, is about the reduced form regression. Now, the reduced form goes by different names depending on the literature and which textbook your lecturer is using. In program evaluation, it's often called also the intent to treat effect. It measures the effect of the instrument on the outcome directly before you scale it by the first stage. And the full procedure of recovering the beta hat with the formula that we just learned here is also sometimes called indirect least squares or ILS, but that is a full procedure by itself, and I'll dedicate a short video to the relationship between ILS and 2SLS and the reduced form, including when they agree and they don't agree. So just make sure that you don't get them all mixed up together. Okay, now why does the Wald estimator make intuitive sense? Think about it in terms of what we're measuring. Z moves by X with like pi 1 hat units. That same movement in Z causes also Y to move now instead by gamma 1 hat. So the effect of 1 unit of X on Y is basically the ratio. So we never directly manipulate the X, we manipulate the Z, and the scale, then scale the effect on the Y by how much Z has moved X. So we're always keeping that channel, Z, X, Y, okay? And that scaling, okay, is the key operation of the IV. If I were to do a numerical illustration of this exercise, keep in mind, let's assume for a moment that you're living 10 miles closer to uni, which increases education by 1 year, okay? That means that your pi1 hat is actually 1. Now, also, suppose for a moment that living 10 miles closer to uni increases earnings by 3,000 pounds. Okay, so what that means is that gamma 1 hat is actually 3,000. Then beta 1 hat IV is actually going to be 3,000 divided by 1, which is ultimately simply 3,000 pounds. What I have done, or what I'm saying in here, is that one additional year of education caused by proximity to a university increases earnings on average by 3,000 pounds. Okay? If the first stage was weaker, then your beta 1 IV would have been something, let's say 3,000 divided by 0.5. So assuming that it's weaker, so not 1 year, but 0.5, then it means that you're gonna have additional of 6,000. So the weaker the first stage, the larger the scaling, and the more sensitive your IV then becomes to sampling noise. Again, this is the problem of the weak instrument in a nutshell. So if pi1 hat approaches 0, then the denominator collapses and the beta IV basically explodes. Okay? That's why a strong first stage is always very desirable, almost not optional. Now, IV estimation works by asking two questions, okay? How much does Z move Y and how much does Z move X? The ratio of these two answers is the causal effect of X on Y, again, using our channel Z, X, Y, and scaling. The IV estimator beta IV, being covariance of ZY divided by covariance of ZX, recovers the causal effect by scaling the instrument's effect on Y by its effect on X, and this way bypassing that endogeneity in X. I hope this video was helpful to get the intuition behind the algebra of IV, and stay tuned. I'll see you in the next video.